Okay, Assalamualaikum and salam sejahtera. So for this video, I'm going to discuss the theoretical part and also the experimental part for the experiment number 5. As you know, we cannot run the experiment number 5 because the equipment was actually broken down or under commissioning. So for this video, I'm going to discuss with you the theoretical parts behind the experiment number 5 together with the, the experimental parts for the experiment number 5. So something is missing here. Specifically, this one is a determination. So experiment number 5 is actually the determination of change in flow speed within a tubes. So before I'm going deep into the experimental parts, so I would like to discuss the theoretical part first. Yeah. So let's assume that we have a fluid. Let's say I have a pipe over here, and then I'm interested with this point, and then end this point. So let's label it as point A, and then here as point B. And then inside the pipe here, I have a fluid. Let's say I have a water flowing from the point A to the point B. And then as already been covered during the discussion on the experiment number 4, basically we have from the principle of conservation of energy, we can say that total energy at the point A is actually equals to total energy at the point B. But then we know that the energy can be either kinetics, potential, pressure energy, and etc. And then from this equation, basically, we already derived this equation. Pressure at the point A over rho G plus ZA plus VA squared over 2G is actually equals to PB over rho G plus ZB plus VB squared over 2G. And then this is known as Bernoulli's equation. Also, if you notice that this Bernoulli's equation is only applicable if the fluid was flowing from one point to another. For example, in this case, the fluid or the water was actually flowing from the point A over here to the point B, which is over there. So, and then, but even though the Bernoulli's equation was actually the basic equation for the fluids, which is flowing or moving, but this Bernoulli's equation got so many assumptions. For example, let's say, going back to here, let's say the water was flowing from the point A to the point B. If you notice that, definitely some of the water was actually near the wall over here. And then because it was near to the wall over here, so let's redraw it, make it bigger. Yeah. So let's say I'm interested with this area. So I have a wall. Oops, I cannot do that. Put it here. Let's say I have a wall over here. This is a wall of the pipes, yeah, and then I have fluid flowing from here. And then definitely some of the fluid was actually in contact with the wall. And then because it was in contact with the wall, definitely it's going to have some losses because it has to use the energy to overcome the friction with the wall. So from this equation, basically, because this equation just simply assumes that there's no energy losses due to friction, but in the real life, basically, we do have the losses due to friction. So now my equation looks like this: VA over rho G plus ZA plus VA squared over 2G minus HL equals to VA over rho G plus ZA plus VB squared over 2G, for which the HL over here is actually energy losses due to friction. Okay, now the HL here can be found by using this equation, F multiplied by L over D multiplied by D squared over 2G. So supposedly the symbol here is quite straightforward. Yeah? For example, the L here, the L over here is the length of the pipes. And then I have D, which is by now you should know that D is actually diameters of the pipe, and then D is actually the velocity. So the only term which is quite new to us is actually the F over here. This F is actually known as friction factors. In order for me to get the friction factors, it's actually there are two ways of finding friction factors. Number one, by using the formula. And then number two, by using a Moody's diagram. Can I use any one of the methods here? The answer will be no. You cannot just simply use any methods here. So in order for us to determine the friction factors, first you have to determine the Reynolds number. This is what you do during the experiment number 6. Experiment number 6. So in order for us to determine, before we can determine the friction factors, basically we have to determine the Reynolds number. So basically here, Reynolds number, RE, or sometimes we use the symbol NR, is actually equals to rho multiplied by D, velocity, rho is density, multiplied by D over mu. And then also, I assume that in chapter 1, we learned that mu, this one is dynamic viscosity, mu over rho is actually equal to kinematics viscosity. So sometimes, depending on which data is given, so sometimes they give you the kinematic. So basically you have to use this formula. So substitute this equation into this one, then I will get something like another formula will be rho multiplied by V over V. Not V, something like this one. So basically here, after I got Reynolds number, let's say after I calculate my Reynolds number, I found that my Reynolds number is actually less than 2000. Therefore, it is a lamina. And then let's say my Reynolds number is greater than 4000. Therefore, it is a turbulent flow. So if it is a laminar flow, then my F can be calculated by using this formula, 64 over Reynolds number. And then if my Reynolds number was actually greater, let's say I get my Reynolds number equals to 10,000, and then I cannot use this formula anymore, because since my Reynolds number was greater than 4000, therefore it is a turbulence. So since it's a turbulence, basically I need to use the Moody's diagram to get my F. So yeah, even though the question doesn't mention that, you have to identify either it is laminar or turbulent flow, but still, basically you have to really understand the concept, saying that, okay, for example, let's say you want to calculate for HL, right? The energy loss due to friction, which is over here. And then the student just simply memorize this formula. Okay, HL equals to F multiplied by L over D multiplied by D squared over 2G. And then you say that, okay, I need to find F. I do remember that the F is actually equal to 64 over Reynolds number, which is here. So if you were lucky, the flow was laminar, then actually you're going to get the correct answer. But let's say the flow is actually not laminar, which is turbulent, then you cannot use 64 over this number, because as I stated here, this formula is actually only for the laminar. So basically, by now you should understand that what is the purpose we are doing the experiment number 6, because basically the experiment number 6, we want to differentiate between the laminar and also turbulence so that we can calculate the Reynolds number. If you remember that during the experiment 6, you put a die, right? So basically, let's say here, put it horizontal lah. And then I put a die, red die here. So I just have a red die over here. So basically for the lamina, you will see that the flow is something like this. Almost a smooth line. So why? Because from here, I can say that my Reynolds number was actually, Reynolds number was less than 2000, which is a small number. So Reynolds number was depending on the velocity. So if my velocity was low, so my Reynolds number should be also low. And then if you also remember that for the turbulence, let's say this is my die injection. So usually I will get something like this. My die was spread chaotically. So this is the turbulence. So that's the reason why we learn about the Reynolds number, so that we can determine which flow was that particular fluid. And then let's say if it is turbulent, then basically you have to use the Moniz diagram. So basically the application of the Moniz diagram you will learn during the lectures, yeah. And then if it is lamina, then it's going to be straightforward. So also basically this one also will be applied in the experiment 7, which you're going to do it next week. Basically, you want to determine the losses for turbulence and also for the lamina flow. All right. So yeah, this is it. Okay. So now I'm going back to the my lecture. So basically, I already covered the theoretical parts. Yeah. So this is the experimental setup. Yeah. If you notice that, as I said before, if you notice that basically here we're still going to use this bench. This is what we call a hydraulic bench. So basically, once I turn on my operating unit over here by switch on the main switch over here, and then the pump over here will suck the water from the tank over here, and then at the back over here it will pass through the pipe over here, and then it will pass through my pitot tube over here, and then it's going back to the tank over here. So basically, once I close this tank, basically what happened here is the water level at this point will be rise. Therefore, actually I can calculate my flow rate, because flow rate is actually equals to volume over time. So usually I will ask during the lab test, yeah, how do I measure the flow rate? By using the hydraulic bench. So this is a hydraulic bench, yeah. So how do I measure the flow rate? So basically you have to explain, saying that, okay, once I turn on my pump, the water inside the sump tank over here will be sucked, will be pumped into the system over here. And then once it come out through the pitot tube over here, and then it will be entering the tank over here. So this tank over here was actually connected to the panel over here. So once the water level inside the tank over here increase, definitely the water level over here will be increased. Basically, you can read. So in order for me to calculate the flow rate, it's actually volume over time. So just let's say I fix time. I want to measure how much the water, how much is the volume of the water for, let's say, 30 seconds. And then I will got the volumes from here, and then divided by time. Basically, that is my flow rates. So this hydraulic bench is basically you're going to do the experiment for the experiment 7 and also experiment 8. So hopefully you'll be able to actually see how the hydraulic bench is working. All right. So in here, so I'm going to concentrate more on the pitot static tube. So basically, as I said before, basically once I turn on my pump, the water will be pumped through this pipe, and then passing to this point, and then entering to here, and then it will be entering to this point. This equipment is called pitot tube. So once the water entering here, basically it will causing the difference in water level. This is manometer. So as you learn in the chapter number 2, the function of manometer is actually to measure the pressure difference between 2 points. All right. So, and then your job is actually, number 1, to calculate the flow rates Q by using the hydraulic bench. Number 2 is to record the height of the water for the point A and also the point B. So going back to here, so basically here, and again, so basically your job is to measure the flow rate by using the hydrodynamic, which is measured. Let's say you fix the time. Let's say time equals to 30 seconds, and then you just measure the water level over here. Then you will get the volume. So the volume divided by time, then you will get the flow rate. So basically your job is to measure the flow rate over here by using the hydraulic bench, and also to record the difference in heights between point A and point B. So basically by measuring the difference in height between point A and point B, basically you can calculate the difference in pressure between point A and point B, which is equal to rho multiplied by G multiplied by H, which is coming from the chapter number 2. So basically this is the schematic diagram for the pitot static tubes here. So basically I have, let's say this is my pipe. This pipe is actually referring to this pipe basically. And then in here, basically I have a pitot tube. So pitot tube look like something like this. As you can see here, I have something like a tubes, which is attached to this one. All right, let's say this is my point 1, and then this is my point 2. Then supposedly I should be able to calculate what is my flow rates or velocity at the point 1 from the schematic diagrams. So let's try. So let's say first I have to draw. So let's say this is my pipe, and then in here, let's redo it. So basically I have a pipe over here. And then okay, and then I have let's say in our experiment, basically we are using water. So basically water was flowing. Let's say this is point 1, and then we actually in the experiment they already installed for you the pitot tubes. So pitot tube is like this. So if I were to draw here, all right, and then let's say this is point number 2. So basically I'm interested with this point and also this point. So as you can see from here, I need to apply the Bernoulli's equation. So my Bernoulli's equation is going to be look like P1 over rho G plus Z1 plus V1 squared over 2G is actually equals to P2 over rho G plus Z2 plus V2 squared over 2G. So from my diagram over here, I can say that my Z1, the elevation of point 1 is actually equals to elevation of the point 2 because the pipe is horizontal. So now I can cancel out my Z1 and my Z2 here. So now I left with this equation is going to be, let me move to the next slide. So my new equation is going to be P1 over rho G plus V1 squared over 2G equals to P2 over rho G plus V2 squared over 2G. Why? Because I already cancel my Z1. My point 1 and my point 2 is actually on the same elevation, which is, horizontal pipe. And then going back to here. So I can see here, my point 1. At the point 1 here, the fluid was actually moving. Therefore, it's going to have velocity. But if you notice that at the point 2 over here, the fluid is actually not moving because it was just like a static fluid. You see, it's not really moving. It cannot move anywhere because as you can see here, there's a wall over here, the wall of the pitot tube. So I can say over here, my V2 is actually equals to 0 because, once the fluid entering this tube, it cannot move anymore because of the small length of the tube over here. So it cannot really move. Then now I have my V2 equals to 0. So what I left here is P1 minus P2 over rho G is actually equals to, sorry, cannot do that. So rearrange everything. Now I have P2 minus P1 over rho G is actually equals to V1 squared over 2G. So let's say I want to find the velocity. So basically my V1 is actually equals to P2 minus P1 multiplied by 2G divided by rho G, or V1 is actually equals to square root of P2 minus P1 multiplied by 2, because I cancel out my G over here, and then now I have over rho. So let's say I want to calculate for the Q is actually equals to, in this case Q1 equals to B1 multiplied with the A1. So this is the most important formula, because I need to calculate for the velocity at the point 1, which is velocity at this point. And then how do I get P2 minus P1? So basically P2 minus P1 is actually equals to rho multiplied by G and then multiplied by H. So this rho is straightforward lah, because we are using water, therefore the rho of water will be 1000. And then we have G, which is gravitational acceleration, which is a formula. So this one also straightforward. And then the H here. So I do know that P2 minus P1 equals to rho multiplied by G multiplied by H. The H is here, is actually the difference in height. So in here, I did have manometers. As you can see in the diagram over here, I have a manometer. So, and again, as I said before, the function of the manometer over here is to measure the pressure difference between point A and point B. So by knowing the height over here, point 2 and point 1, so I minus both two, P2, H2 minus H1, then I'm going to get the P2 minus P1. So this is what the experiment all about. All right, so now my formula will be, my V1 is actually equal to square root of P2 minus P1 multiplied by 2 over rho. So this is my formula lah for the Pitot tube. And then also, if I want to calculate the flow rate, Q1 is actually equals to V1 multiplied by area. And then P2 minus P1 multiplied by 2 over rho. Area usually the pipe should look like a cylinder, right? So pi d square over 4. So usually the pipes look like this. So it's a circle. So therefore I use this formula, pi multiplied by d squared over 4. Then I will get the flow rate. So basically this flow rate I obtain from the calculation over here, I need to compare with the flow rate which I obtained from the hydraulic bench. So let's say my flow rate calculated by using the formula for the Pitot tube is different from the hydraulic bench. So basically that's the purpose of the discussion. Basically we can discuss why there's a difference between the, from the, by using the formula over here and then by using the hydraulic bench. But then if you notice that, hopefully you learned during the experiment 6 and 7, if you notice that the most inaccurate method of measuring the flow rate was actually by using the hydraulic bench. And then reports. So of course the reports. How can the report started with the procedures? Hold on, yeah. Oops. Oh, okay. Most probably I already mistakenly deleted the so let us discuss regarding the reports. So basically the report over here should have cover page. And then also if you refer to the objective in the report, basically they have something like a velocity profile. That one we're not going to run because we don't have the data for the velocity profile. So basically the objective is going to be, should be, objective number 1 should be okay, and then objective number 2 have to be deleted. You have to delete the objective number 2 in the modules. But then, because only one objective look quite short, so usually for the objective number 2, I will say that, okay, to compare the flow rates by using Pitot tube formula, and by using hydraulic bench. So basically I want to compare these two data. and then the objective, and then we have the procedures. So procedures should be straightforward, but then you have to remember that you have to use the persistent terms. And then result and sample. Oh, okay, sorry, before that, introduction. So for the introduction part, usually I will discuss let me go back to here. So okay, I deleted. Okay, Command Z. Okay. So for the introduction part, let's say I would like to do the introduction for this experiment, for example. So usually I will discuss what is pitot tube. So there's one paragraph lah. And then I will discuss, the one can be Google or you can find it from the textbook lah, discuss the working principle of pitot tube. And then I will also find the application of pitot tube in the real life or in the industries. So basically, yeah, usually I will write the introduction about three paragraphs, something like that. So usually for the first paragraph, I will discuss what is meant by the pitot tube. So the readers will have some general idea what is actually pitot tube means. And then the second part, usually second paragraph or second part, I will discuss about the working principle. How does the working principle of the pitot tube? That one can also be Google, but then as I said, as I always highlighted before, usually once you take something from Google, please do some addition. You cannot just simply copy and paste everything from the Google. And also, please do not use the Wikipedia. Wikipedia is not really accepted in the academic world as a valid sources. And then we have the application of the pitot tubes. So you can know what is the application? Usually, where does the pitot tube being used? And then after the introduction, then we move to the procedures. Procedure will be straightforward lah. Usually, I will suggest the student to use the flowchart, and then use the passive sentence, and then result and sample calculation, and then we'll see it on the next slide, right? And then discussion. So I have to move to the result and discussion. So basically for the result, usually your result should look like this, yeah? So basically this one is the typical data, yeah? So first I have the pipe inside diameters. So this one is already given in the module, okay? And then pipe cross-section area. So basically the pipe cross-section area is like this. So if I were to calculate the cross-section area, so area is actually equals to pi b squared over 4. So some students love to use the pi r squared. For them, it's look easier. But then sometimes when you later on when you learn about the fluid dynamics, you will notice that it's not really good for us to convert from the diameters to the radius, because usually the data given in the form of diameters. So usually we just use the whatever given data instead of converting it by divided by 2. So basically here for the pipe cross-section area, I just simply use this formula. And then the water density, this is as I said, the typical value for the water, the density of water is actually 1000 kilogram per meter cube. So and then in here, I got a couple of columns, yeah. So the first column over here is actually the hydraulic bench. So basically what we did here is we just measured what is the volumes of the water for the given time. For example, let's say here, because the volume of water is quite high, therefore I use 30 seconds instead of using 1 minute. So what I did here is I just set the timer to the 30 seconds, and then I just measured the volume of the water. This one is from this one, yeah. So basically here, so once I turn on my pump over here, and then the pump will pump the water from this tank, and then entering to this pipe over here, and then passing through the pitot tube, and then it will come out here. So usually we close this the valve over here. Let's say I want to measure the flow rate. So basically I just close the valve over here, and then the water level here will be rise. And then this tank was attached to the panel over here. and then it will give you the volume at any given time. So let's say I set a 30 second. After 30 seconds, I just simply measure the volume over here, and then the volumes over time that is actually flow rate. So hopefully you'll be able to understand this one. This one quite straightforward. So in order for me to calculate the flow rate, it's just simply volume divided by time. Then I will get the flow rate by using the hydraulic bench. And then the pressure head here is just basically I just measured the height of the water at the point A and also point B. So basically here, so what I do here, oops. So what I did here is just, this is my beta tube. So once the water was pouring inside here, it will give a pressure difference. And then the water level here will rise at a certain point. And then let's say this is point A, this is point B. So at any given experiment, I will just simply record what is the height of the water inside here, inside the manometer. So this is where does the data coming from. So this one is just a recorded data lah. And then in order for me to calculate the hydraulic pressure over here, so from the chapter 2, I don't know that pressure at the point A equals to rho of water, which is this one, multiplied by G, and then multiplied by H. The H here is coming from this one. So same goes for the pressure at the point B. PB equals to rho of the water, which is 1000, multiplied by G, and then multiply by H. And then because I'm referring to the point B here, I cannot just simply, okay, I want to take, this time I want to take the HA. I cannot do that because PB with H is actually referring to the B. So I have to use the HB. So basically the HB here, just obtain from this data. And then they ask you to calculate for the, so basically this is how we come up this one. I already show you how to get the PA and also PB. And then here we got the delta P. Delta P here is just simply PA minus PB. So quite straightforward. We just want to know the difference, the difference in pressure between point A and also point B. So I just calculate for this one. And then now here, I need to calculate for the velocity. In order for me to calculate the velocity, which is at the point A here, I have to use the formula. Oops, already lost. Is it? No. Yeah, I have to use, in order for me to calculate the velocity at the point A, so from before, I already derived actually, yeah. So I have P minus PA multiplied by G, or no, multiplied by 2 over rho, and then the rho here is density. So I can use this formula to get the velocity at the point A. So once I calculate the one, I can just simply put a value over here. And then once I know the velocity, actually I can also calculate the flow rate. So basically before this, I already calculate the velocity, right? So let's say my velocity is coming from this formula. V1 equals to P2 minus P1 multiplied by 2 over rho. Let's say I got the velocity here equals to, for example, 3 meter per second. And then I need to convert from the velocity, I need to calculate the flow rate. So basically the flow rate is actually equals to velocity multiplied with the area. And then if you notice that the unit for the flow rate is actually meter cube per second. And then let's say suddenly you say, okay, I do know that my flow rate, and then I do know my velocity. And then what is the relationship between flow rate and also velocity? So from unit, basically you can determine what is the relationship. For example, the flow rate, the unit for the flow rate here is meter cube per second. And then velocity, velocity should be standard, right? Meter per second. So now I have meter cube per second and meter per second. So how do I get this one? So basically I have to multiply with the meter to the power of 2. Meter multiplied by meter power of 2 is going to be meter power of 3, which is flow rate. So now I know Q is actually equals to A multiplied by B. B multiplied by A lah. So once I already got the velocity over here, I just put it here, and then I calculate for the area. Area, as I said before, the pipe usually in the circle. So pi d squared over 4. Then I get the value of Q equals to, let's say, 7 meter cube per second. But then, if you notice that, Oh gosh. Okay. Okay. So if you notice that the calculated flow rate here, they want it in the unit of liter per minute. So basically, you have to do the unit conversion to get the flow rate, because the reason why we use liter per minute here, because in here, usually the unit are liter per minute. You cannot compare if one in liter per minute, another one will be liter per second. It's very difficult, of course, to compare. So we have to make sure that the flow rate are the same unit. All right. And then definitely the calculated flow rates by using the Peter tip here is going to be different from this one. So it is the function of the discussion. Really, we discussed why did our calculated value are slightly different from the measured value by using the hydraulic band, for example. And then really will suggest the improvement. How do I get the better result, closer result from the calculated value and also the measured value, something like that. So this is the function of the discussion. And then we just do the conclusion. Usually the conclusion should be answering your objective. And then we have reference. And then minimum reference should be 5. And then for the reference, really we use the APA methods. So if you don't know what is the APA method, you can ask Mr. Google. So I think that's all for the experiment number 5. So usually I will give you 2 weeks to complete the experiment number 5. And then if you have any problems, you can contact me and then I'll try to help you as much as possible. All right, guys. Thank you very much.